The terrible one?
Yeah.
Okay, no, that's fine. That's fine. We can definitely do 31. Are there any other? I mean, are there any other ones besides 31 that we can do like as a warm up, or do you want to go straight to 31?
23.
23 is 23 awful as well. Are you guys picking good ones for me? 23. Okay, we can do 23. That's fine. I like 23. 23 is a good one to start with. So what's it asking you? It says, use the properties of geometric series to find the sum of the series. Nice. For what values does it converge and which values does it not converge? That's a great question to do. I like that one. Okay, so this is a good warm-up one. I like this one. So first of all, is this a geometric series?
Yes.
Yep. What's our A value? Our A value is what? What's the initial value? Someone said it already. Yeah, A is 4. Good. And I know the book likes it. What variable does it like to use for the ratio? It does in some places, but in some of the examples, it uses X as the ratio. I don't know why. Like that makes no sense whatsoever, right? It's terrible. So let's just say R is, the ratio is, what is it? It's Y over what?
3.
Y over 3? What's fascinating about that is this. Now let's just look at what we said there. If A is the leading term, that's what A is supposed to be, right? If the ratio is Y over 3, it makes sense to go from here to here, you multiply by Y over 3, right? To go from here over here, what do you go from? Y over 3. But how do you get from here to here?
So 4 plus.
Exactly. So excellent. The first thing you have to realize is A is not actually going to be 4. A is going to have to be Y, and then you just tack on 4 to it. That's a great thing to realize right there. Okay, so in this case, we're looking at just this, and we're going to add 4 to it at the end. So our A value is going to be Y. So if we wanted to find that sum, it was the initial, what was that formula? The initial term times 1 minus what?
Y over 3.
To the n, all over what?
1 minus
Y over 3.
plus 4.
Plus 4. Correct. So what is this asking us about? What is this question asking us to do? So we're supposed to find the sum, so we need to compute this limit, right? And then but it asks us something even more interesting after that. What does it ask us?
So what values of Y
Does it converge, right? So like what values of the variable does it converge? Okay, so do you want to do the limit right now and see what happens? Does that sound good? Do we calculate? Is now the time to calculate a limit? Yes? Come on, have some confidence here. It's okay if we don't do the right thing right now. This might be right, it might be wrong, but you're going to tell me. We have this expression right here, which this limit, the limit as n goes to infinity of this thing is going to be the sum that it's asking us for, correct? So if we were to calculate this, what happens? If we want this to actually converge, we know that the absolute value of the ratio has to be less than what? 1, right? But what is the ratio in this case? Y over 3, right? So we know that Y over 3, the absolute value of this has to be less than 1. What does that mean? That means that Y over 3 has to be less than 1 or greater than, not equal to, I don't know why I put that in there. Greater than what? Negative 1. So therefore, Y has to be between 3 and negative 3. Exactly. So now, are we done? And we answered what it'll converge when Y is between those values, correct? But what else is the question asking us for?
The sum.
The sum. So when it converges. So our answer is probably going to have what in it?
Y.
It's going to have Y in it. So how do we go about doing that? Plug in any what? So here's the thing. Hold on. What's the only term up here that might cause us problems with evaluating? What's the only one that we're most? Which one are you most worried about? I'm worried about this one in particular, right? But here's the thing: if Y over 3 is greater than 1, we know it's going to diverge, and we don't care what the sum is because the sum doesn't exist, right? But if we know it converges, we know that Y over 3 is less than 1, right? So raising it to the nth power, what happens to it?
0.
Yay! So you know if it converges, if it converges, this thing goes to 0, right? So what does that allow us to now do? Simplify. There it is. We allows us to simplify. Excellent. So we end up with, if I remember this correctly, we have Y times, I'm just doing 1 minus 0 just for completeness, all over 1 over Y minus 3 plus 4, right?
That plus 4 is kind of a tricky little wicket. Now, one thing you'll notice if you ever look up answers for questions like this in the back of your book, they tend to simplify it down like completely and utterly. So you're not going to see an answer written like that, right? They're probably, I haven't looked it up, but they're going to write it. You don't have to?
Do we?
Well, yes, you should. I mean, in this case, yes, you should. So let me be clear. Sometimes the book, I think, oversimplifies. In this case, you should. I don't like seeing compound fractions like that. So this is going to be what? 3 minus y over 3 plus 4, right? So that equals 3y over 3 minus y plus 4. Is that correct? Help me with that. You flip over the fraction, yeah.
Right.
Now, I would stop there, but I wouldn't put it past the book to do something weird and turn it into something else. So when you look something up in the back of the book that you're relatively sure is correct, and you look at it and you're like, that is not what I have, take a second to see if it actually is. I'm serious, the book comes up with some really crazy, I mean, it's interesting sometimes. You're like, oh, I learned something. And other times you're like, you pissed me off. We multiplied it by 1 plus 0.05, and that gave us what? 105, right? But let's say we don't know what our amount is, right? And we know what our rate R is, and that's going to equal what? The total n, right? So what does that mean A is? N over 1 plus R. So the amount we start with is going to be the amount we want over 1 plus R. And how many years did we just do this for? How many compoundings did we do this for? We did it for one compounding. We did it for 1 year. So the question is, how does this change if you have multiple years? What do we have to account for if we were compounding for multiple years? Well, let's go back. So this is 1 year. Let's go back to our original example, right? If you have $100 and you compound it once, it's this, right? But if you compound it twice, what happens? So this equals the amount of money you have in your bank account if you start with $100. No, you square it. You just square it. You do it again, right? You just square it. This right here represents the amount of money you have in a bank account if you started with $100 and the interest rate was?
Oh, for 2 years.
After 1 year. If I just wanted it for 2 years, how much money? Yeah. How much money would you want after 2 years? You would just square it, right? No, you're absolutely right here. But here's the thing. So let's generalize it. I'll keep that up there. So this is like the semi-generalization, like this. So what's our general A going to be? If the final amount you want is n, it's going to be 1 plus r, but what are we going to raise this to? Whatever number of years you want, right? 1, and then 2, and then 3 years out, and then 4 years out, and then what? 5 years out, and then n years out, right? So you can kind of think of it like this. So you're adding all these up. Now here's the thing. That's actually really good for us because if we list out all these terms, if we list them all out, you'll have n over 1 plus r, and then you'd have n over what? 1 plus r. And why is this structurally good for us to see? Because what kind of series is it? It is a geometric series. It is a geometric series. You with me so far, everybody? Now here's the thing. So we've generalized it to compound interest. But we haven't generalized it quite enough yet because what type of interest do they want us to use in this question? Continuous interest. Continuous interest. Do you remember what the formula for continuous interest is? A equals what? Yeah, you said it right. What is it? There's no over. It's actually, there's no fraction in it, which is really nice. Yeah. So if you want, I'm sorry, I wasn't clear. The general formula for continuous interest is PE to the RT, right? So this right here represents the amount you get when you put a certain principal into an account at that interest rate for that number of years, right? So what we're really interested in is this P right here. What is the principal? Or what another thing called present value, right? Because look, if we want to, here's a question. If I want $1,000 in my bank account after 10 years of a certain interest rate continuously, you would figure P. You want to figure what you want to put in to begin with, right? So what does P equal in this case? Yes, exactly. A over what? To the RT. Exactly. E to the RT. So what's the, now here's E to the RT. What's our interest rate on this? It tells us. Now we can actually start putting values in. What's our interest rate? It's 4%, right? So if it's 4%, how do we write that? 0.04, right? So our terms here, so amount, what's the target amount we're always looking for at the end of the year? So if we look at it in terms of the amount of trees we're selling, what's the A value always going to be in this? It's going to be 1,000. Now let's just pause for 1 second. Are you with me so far in what we're doing? Are you with me so far? Kinda? We're pretty good so far? Okay. So if we want to actually do this, we need to figure out what the ratio is between terms. Be really careful. What do you think the ratio is? So here's one term. I'll give you an example. E to the 0.4, right? Thank you. That is not, I don't know why it does that sometimes. Yeah, that would be a 40%, and that would be good or bad. I don't know. I'm not sure. 0.4, right? What's the next term? It's 1,000 over what? E to the 0.04 what? Oh, not. What happens? What happens to this? This doubles, right? Times 2, right? Because it'd be 2 years. That would be 2 years out. That would be the $1,000 you want in there at the end in 2 years, right? So what's the ratio between these two? So the next one, what's the next one? Just so you can get the third, sorry. 1,000 over e to the 0.04 times 3, right? Is there a constant ratio? Yeah, there is. What's the constant ratio going to be? Yeah. So another way to say it is e to the negative 0.04. So this right here is our ratio, right? So if we take that all together now, we have a formula for the sum of an infinite series, right? What's our initial value? What's our A value? We already decided what it is. It's 1,000, right? And we know our R value is 1 over, we don't have to say 1. We can just say e to the negative 0.04. So what's the sum going to be? 1,000 over what? 1 minus e to the negative 0.04. Exactly. So at this point, what do you have to use? Tina's like, I can do that in my head. It's like, you've graduated, leave. You know, like, no. Can someone do that on their calculator and tell me what that comes out to be? You know what? Yeah, just verify. It'd be nice if you could take out your calculator and verify. It should come out to be this right here. There. What do you get? P is equal to 1,000 divided by e to the that layer got moved to the what? To the 4th, right? Do that on your calculator. Tell me what that is. So this is what's the present value of $1,000 in 100 years at 4% compounded? $18. So do you see how small that gets so quickly? So what that means is if you put $18 into an account right now, compounded 4% continuously for 100 years, you would end up with $1,000, right? That's why the present value is actually bounded. It's finite. At first, this question made no sense to me. Like, infinity dollars. I'm like, no, that's not what it's asking. We have this symbol. What's that symbol called?
Sigma.
Sigma. We're summing up a lot of things. So a partial sum as opposed to an infinite sum. What's a partial sum going to be instead of an infinite sum? What's the simplest way to say it? It ends. It ends, right? It ends. Yay. So what we're going to look at is like the sequence of partial sums. So the first term, then the first 2 terms added together, then the first 3 terms added together. And we're going to look if that sequence converges. Because if the sequence of partial sums converges, then we know the sequence converges. That's effectively what we've been doing. The big kid math way of saying that is if the sequence Sn of partial sums converges to S, so the limit of n as n goes to infinity of Sn equals S, then we say the series converges. And that its sum is S, we write rah, 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 rah. You know this already. It converges if the sequence of partial sums converge. It's fun. Mathematicians like to write things totally properly, which is totally fine, but you understand this right now. You've done this. You understand the idea that if the limit of the explicit formula for the sum of an arbitrary number of terms converges, then the series itself converges. Yay, it's exciting. So what's nice is we need some properties to use so that we can attack convergence. So the first one is this. If you have two series that converge, and let's say k is a constant, what happens if you add them together? If you add together two convergent series, what happens? They converge, right? Converges to the sum. The sum of the summation is the summation of the sum. You can break it apart. Oh, what happens if there's a constant times every term? What can you do with that? You can bring it to the front. These are just relatively straightforward.
It's like integration.
Yes. It's like almost perfectly analogous because that's what integration is, an infinite sum. Yes. Changing a finite number of terms in a series does not change whether it converges. This is really cool. So if you have an infinite series and it converges, if you only change a finite number of them, you can do anything you want to a finite number of terms, it'll still converge, which is pretty cool. Okay. If the limit as n goes to infinity of an does not equal 0 or the limit does not exist, then it diverges. So here's the thing. If the terms that you're adding together don't go to 0, if you add them all together, what happens? Like what's 1 plus a half plus a half plus a half plus a half plus a half? It's always going to blow up. For a series to converge, the terms need to go to 0. Does that kind of make it sense? If you add together an infinite number of things that aren't 0, if it doesn't go to 0, then it's going to blow up. On the last one here, if the summation diverges, then any multiple of it diverges. As long as k isn't what? It's the last one here. 0. What happens with 0? You can basically break any rule you want with 0. 0 is a great. Does this series converge? What's the first term in this series? What's the first term in this sequence if we listed it? If you plug in 1, what is it? Well, it's going to be, let's say n is greater than or equal to 0. Sure. So if n is 0 here, so n and then the value. If n is 0, what does it come out to be? 0. If n is 1, what does it come out to be? 1 minus 1 over e, right? And then if it's 2, what is it? 1 over 1 minus e squared. So here's the thing. If I asked you, if you take all these terms right here and you added them together, is the sum going to converge? Is the series going to converge? What do you think? Does it go to 0? Ah, we have some shaking hands. It goes to 1. Good job. That was good harmony there. He's shaking his head no, and you're saying 1. Look, what happens to this term? What happens to this term right here? That becomes smaller and smaller and smaller and smaller. But what's always sitting out front? 1. So when you add these all together, is this going to converge? No, because the individual terms don't go to 0. Bless you. What about this one? This is a fantastic one, and this is one we're going to talk about for a little while. We saw this one before. Did anybody come up with a name for this? Begins with an H? No? Really? So do the terms go to 0? 1, 1/2, 1/3, 1/4. 1 over n goes to 0. But if the terms go to 0, does that mean it has to converge? No. It's necessary, but it's not sufficient. The terms have to go to 0 for the series to have a chance of converging, but just because they go to 0, does it mean it has to converge? No. So this is a really, really key one because you're going to use this to compare other series with. What are your thoughts on this one? Do you think this one converges? Effectively, are those terms getting small enough, fast enough for the sum to converge? What do you think? What's your feeling? Who thinks it converges? Who thinks it converges? Who thinks it diverges? So for it to diverge, it means that has to be as big as you want it to be. So it's an even split, you're not quite sure? That's fine because I think that's really what it should be. Unless you've proven this, it's not clear. And that's the message I want to drive home here. You're going to look at series sometimes and you're going to think like, oh, this clearly converges, and it definitely doesn't. So be careful. Be careful. There's a really cool picture here that helps us do this.
This blue function is the function 1 over x. You looked at that function before? What's the area of this first box right here? 1. What's the area of this second box? 1/2. What's the area of this next box? 1/3, right? Oh, so we have 1, 1/2, 1/3. So could we keep on doing this? Okay. This is the left-hand integral for something that's concave up, right? Is this an overestimate or an underestimate?
Overestimate.
This is an overestimate. You with me so far? Okay, so what does this tell us? This tells us that the sum, n equals, let's say, what did we say? Yeah, 1. 1 to infinity of 1 over n is definitely going to be greater than the integral from 1 to infinity of what function? What was that? 1 over x? Are you okay with that statement right there? You okay with that statement? We're good. So we're not quite sure about this. That's what we're trying to analyze, right? We don't know about that yet, but what can we analyze? Ah, now what type of integral is that right there? Remember how you do an integral like that? You might have looked at no. You have to anti-differentiate, but what's the symbol? There's a problem, or not a problem. Something you might not have seen before. The infinity thing. Raise your hand if last year you saw something like this. Have you ever seen that before? Maybe you might have seen it a little bit last year. We're going to talk about this. It's fine. But the idea is, can you quote unquote plug in infinity? No, you can approach infinity. So that's what we're doing. We're going to evaluate this integral. We're going to plug in 1, we're going to plug in n, and then we're going to evaluate the limit of it as n goes to infinity. Okay? What is the antiderivative of 1 over x? ln of x? For value. Yeah. Okay. And do we have to take the absolute value in this case? N's going from 1 to infinity. I'm just cleaning it up. Right? In this case it is. So what is this? This is going to be ln x, right? From what? 1 to n. And we're doing this. We're doing the limit as n goes to what? Infinity. Okay, so we have to plug in n, plug in 1. So you get the limit as n goes to infinity of what? ln of n minus ln of, what is ln of 1? So this thing right here, this limit right here, sorry, the button is being a little uncooperative, goes to the limit, because this goes to 0, n goes to infinity of ln n, right? So what does this tell us? As n gets bigger, what happens to ln of n? It also gets big, right? Gets huge, right? So what does this equal? We can say it blows up, right? Okay, so we just showed that this right here blows up. But what do we know? We know that this series is greater than the thing that blows up. So what does this have to do? It blows up as well. So here's the deal. If you're above something that diverges, it's diverging, right? If you're below something that converges, it's going to converge. So you can find floors and ceilings that work really well. This is a really good one. So now you know that this series, what does it do? It blows up. It diverges. It's kind of cool. That means that if you pick a billion, there's a certain number of terms you can add together and you will get to a billion, which is kind of cool. So, let's keep going here. What about this one right here? This is a cool one. What's the only difference between this one and the one we just did? What is it? It says this one it tells you it converges, right? It says prove that it converges. So what did I say? If you want to prove something diverges, you need to find something it's greater than that blows up, right? But if we want to show that this converges, we want to find something that this is below that converges. What function do you think we're going to use as a ceiling? 1 over x squared. So here's the picture of this one right here. This one right here, right hand, concave up. So this is an underestimate, right? It's lower there. So if you do the same thing, if you integrate from 1, you do the limit as n goes to infinity of this integral right here, guess what happens? You get a number. So therefore, if this is less than a number, what does this have to do? Converge. It's kind of cool. I'm not going to do out the math. You can do the integration out yourself if you want to. So what you see is this. If it converges, so if you have, suppose that a and f n where f of n is a decreasing and positive, if the integral converges, then a n converges. If it diverges, then it diverges. So this is one way of summing up what we just learned, which is if you have an integral that you're above and it diverges, it blows up. I like to say blows up as well. If it's below, it will converge. Yay, it's exciting. So let's do a couple of these. I think we have a couple minutes here. Actually, we're just going to get to the sum of this because I think we have 2 minutes, so I don't want to go in too much detail, but I did clip in the 7.7 thing for you here. These are the series that we just talked about. We talked about P series right here, and we mentioned this before. We did 2 different ones. The first one we did, P was equal to 1, right? It was 1 over x. And did 1 over x, did that converge or diverge? It diverged, but when it was 1 over n squared, what did it do? It converged, right? So P series. And I think I mentioned this before, but I'm very clear about it now. This is the truth that you get to work with, which is super cool, which is the P series, 1 over n to the P, it converges if P is greater than 1, and it diverges if it's less than or equal to 1. And if you want to look at the math, you can definitely follow it. I clipped it in for you. It's from back in 7.7. What you do is you do the integral on the general case. It's not that bad. You can do it piece by piece. It really isn't that bad. You do the integral on the general case, and what you show is exactly what this says. It will converge if P is greater than 1, and it'll diverge if it's less than or equal to 1. But this is really useful because you will use this to prove bigger, nastier things, converge or diverge. Because one thing that you need to remember about math is you might see something with a really big, nasty problem, but if you can break it down into small pieces and do each small piece, it becomes much easier. Okay, so you have your homework. It is listed in Schoology. It's due on our next class, which is Thursday. It's our 9.3, and you have to do your journal entry.